Okay, so we're gonna start. We're gonna start the lab. So as some of you or most of you should know, Zico is out all week. So I will be giving a tutorial today on the basics of Jupyter and Python and some basic visualization techniques that you can use to plot stuff and basically, all the stuff you need to know to get started with working on the homework. Okay? So basically, this is just an outline. We're going to quickly run through how you would set up your notebook environment. We're going to go through how you actually use the notebook interface. So like how you can run code, test code, etc. And some tricks that you can do. And at the very, very end, there'll be some like common questions that we've had over and over again. Just some announcements. For your future planning, the project proposal is going to be due on October 19th. It's going to be maximum 1 page. It cannot be more than 500 words. There's a lot of you, so don't make it too long. It's really just to say like who you're working with, what you want to do, and maybe what data set you want to get or collect, just so we have an idea of what you want to do for your project. And so the thing that you should probably start doing is find your teammates if you don't have any groups yet. And if you are having trouble finding teammates, I suggest that you use the Piazza search for teammates post. It's pinned, it's at the very top. It might be underneath some other pinned posts, because there's a lot of pinned posts, but it's still pinned. So find some teammates now, and the proposal is going to be due about a week after the schedule says the project is out. Okay? And then the lunch signups with Zico are going to be released shortly on Piazza. I think we'll probably we'll post the link to a spreadsheet at around 4 p.m. today. This will be accompanied by an announcement on Piazza. And basically, you just go there, and then you find a day that you'd like. You can put your name on it. And then please put your name there only once, because there's a limited number of slots. And the way Zico's going to do it is if there's too many people on a particular day, he'll randomly pick 5 people. Okay? So try to disperse yourselves evenly throughout the sign-up slots. And some reminders. Homework 1 is due next Wednesday, and we have office hours. They're right there. They're also on Piazza. Typically, what I found that is happening is that there's always more than a couple people. So actually, they'll be right outside the office, usually in the common area of the Gates building. Okay? All right, so now let's get started. Before we begin, are there any questions? Yes?
These nodes are open during the hours, right?
Yeah. So the question was, what if we don't have access to the Gates building? I believe all of our office hours, actually we can see right here, all of our office hours are on weekdays before 6 o'clock, which means that everybody has access to the upper floors of Gates during that time. So you shouldn't have any problem getting in. Okay, any other questions? All right, so let's get started. So for those of you that haven't started the assignment yet, you will need to have an installation of Python on your computer so that you can write, so you can test and write your code locally. It's a lot easier to do it locally as opposed to remotely. And for this course, we could recommend that you use this package called Anaconda, which is a scientific computing platform that contains almost every single tool that you'll probably need. There are a few exceptions, so every now and then we'll tell you to run an installation of a new package. But for the most part, this should contain everything that you need, and they'll all be linked together, so you don't have to really worry about it. So you can download the 2.7 version here. Make sure you're using Python 2.7 and not Python 3, because we're making this decision because not every single scientific computing package has moved on to Python 3. So unfortunately, for those of you that have already learned Python 3, you're going to have to go back a little bit to 2.7. But it's not too different, so you'll be OK. And you can verify that you're using the Anaconda platform by just starting an interpreter, and you should see that it's a little small, but you can see, you'll see the word Anaconda in the interpreter if you're using it properly. So sometimes we'll need more than the default packages that come with Anaconda. And so if there's a conda package for it, we highly recommend that you just use the conda install command so that you have the least amount of problems when you're installing these packages. Okay, and then, for example, at some point we'll probably use the PyMC module, and so like you would use the corresponding conda command. We'll have this like in the write-up of every homework. So if you ever need to install something, then we'll have what you need to run to install it. And if it's not on Anaconda, then usually it'll be on pip, which is a package repository for Python packages. And for example, in the first assignment, you'll need Yelp Python, which is not in the Anaconda package. So you'll need to run a pip install Yelp. Okay? Yes? So the question was, does it work on Windows as well? And the answer that I have for you is yes, because I have run everything on Windows. It also works on everything else, but it's notoriously harder on Windows, and I've made it work. So it does work. Any other questions? Okay. All right. So the assignments for this class, as you know, are distributed in Jupyter notebooks. And so we're doing this because they let you create documents that are a mixture of both write-up and code. And we're going to walk through a notebook in a little bit, and you can read more about it at this link. But you know, you can do all of your development, you know, all your code writing, all your testing. You can do your debugging. You can do that all within the Jupyter environment. So if you're unfamiliar with it right now, and you've tried to do the assignment, and you've been writing like your test code in like a separate full file, you can keep doing that if you want. But it is a lot easier to do just have everything in the same notebook. And so when Jupyter Notebook comes inside Anaconda, so if you've already installed Anaconda, then you're all set. All you have to do is run Jupyter Notebook, and then that'll launch your live Jupyter interface. Okay, so now we're going to basically go to a notebook and sort of walk through the type of things that you need to know how to do. Okay. So I'm going to run the Jupyter Notebook command here. Let's see. It's not too important. It's just the Jupyter Notebook command. Okay, and then you'll see it launches launches a web interface, and you basically just navigate to your notebook file, and you can click on it, and it opens the notebook. There we go. Okay, so for this, I'm going to start from scratch. Okay. So some basic Jupyter Notebook 101 is that the sections of the notebook are organized into cells, and these cells are marked as Markdown or as code blocks. So like this very first one is just Markdown. We wrote it for you. It's just to give you some description of what's going on. This second cell is a code block. So in order to run code blocks, you would need to hit Shift-Enter, and it runs the code block, and the output is listed underneath. You can click on the output, and you can modify it however you like. And then you can rerun it again with Shift-Enter. Okay, so you can keep changing your code and keep rerunning it. And you can add more cells or delete new cells. You can do that with like Insert. There's Insert Cell Above, or you can use the shortcuts. It's like A and B. You press A to insert a cell above. Then you can type more code there. You can run it. And then you can press B, insert cell below, etc. So in this way, you can write all your code in the notebook, and you can also write your tests in extra cells in the same notebook. So you don't have to keep moving around in different files. Okay, so that's the basic notebook sort of editing. And if you need to know more, they have this help user interface tour, which will actually walk you through every single possible feature that this notebook has. We won't do that right now. I'll let you guys do that if you want to. And they also have this keyboard shortcuts, which I recommend you use because it's just a little faster sometimes to use the keyboard shortcuts. Okay. So, are there any questions on how to use the notebook? And you all know that to submit to AutoLab, you just submit these notebook files to Autolab in a tar file. There's been some confusion on Piazza. Just tar the notebook files without any sort of directory structure, and it should process fine on Autolab. For that future assignments, we're going to give you a make file so that you can just run make and it'll tar it for you in the proper structure. Okay. So if there are no questions, do you have a question back there, or are you just raising? Yes?
For the Autolab, can you upload as many times as you want, or it's just whatever your final?
You can upload as many times as you want. Your final submission will be the one that is graded. That gives you your grade. And there's no grading beyond Autolab. So we're not going to grade you for style or anything. So whatever you see on Autolab is your final score.
So if you've only completed part of the assignment, but you want something that's right, you can upload that.
Yeah. So your question was, if you want to do only partial submissions, you can do as many partial submissions as you like, and you can see your grades as you've got, as you are completing the notebooks as you go. One note for the XML parser, it's necessary to complete the entire notebook before you can get a grade. So there's that. Because we only test the final output of your XML parser and not the implementation details. Okay, any other questions? All right, so now that we've covered how to do the Jupyter, how to work with the Jupyter notebook, we're going to walk through some basic list or basic Python things that you really need to know. Is this too small? Should I make it bigger? Here we go. Let's do that. All right, is this big enough? Okay. So Python is an interpreted language for those of you that have never used it before. And so that means you'll mostly be writing your code and running them as scripts. The two basic data structures of Python are basically lists and dictionaries. So we're going to start with lists. So for many of you, this will probably be a review. So I apologize in advance. But for some of you that have never used Python, I hope you find this useful. So lists are sequences of objects that are denoted by the bracket notation. And so you can initialize a list by directly specifying their elements, as you can see here. These elements do not have to be the same. They can be whatever type that you want them to be. So we have a list, an empty list. We have a list of characters. We have a list of integers. We have a list of strings. We have a list of a mix of elements. And just running this cell just creates these lists and prints them out. And you can see that that's what happened. Also, just one note, side note. This notebook is on the course website, so if you want to, you can also download it and go along on your own computer if you have your environment already set up. Okay, so now you can index into lists using this start:/stop:/step notation. So the start tells you where to start in the list, the stop tells you where to stop, and the step tells you how many elements to skip every time you take a step. And this also just sort of demonstrates what happens when you index into this list. A colon without anything will retrieve all elements of the list, and then this one will get everything from the first element to the end. This third one will get everything from the beginning to the second element, and then you can also give it negative indices. Python understands that, and it just goes backwards. And here's an example using a step from the 0th entry to the 3rd entry, taking a step size of 2. Okay, so hopefully this is a review for everybody. And then there's also these things called list comprehensions, which is a different way of creating lists. And so you can create a list with a sort of a for loop. And so, for example, here we're creating for every integer I in list 3, we're going to create a new list that has 10 times the integer I. Okay, and so that creates the 10, 20, 30. Or for every string in list 4, we're going to create a new list that has the length of the string. Okay, so these are sort of convenient ways that you can write your code. It tends to be a little faster than writing for loops to iterate and create and append the new list, append new entries to the end of your list. So I recommend that you do this for the maximum efficiency. But if you need to, you can iterate over a list using a for loop, for example, in this cell. We print every string inside this list. Okay. Any questions about that? Okay. All right. So in this example, what we're going to do is I downloaded the entirety of Shakespeare's work, put it into a text file, and so basically what this is going to do is it's going to open a file, and it's going to read all the lines of that Shakespeare text file, and just print the length of the resulting list of lines, and also print the first 5 lines. Okay? And so we see that there are like 111,000 lines in the Shakespeare text, and the first 5 lines are, as you expect, the Act 1, and then the first few lines of it. And so putting this together with what you know about lists, we can count the total number of words. So in this Shakespeare variable, it's a list. You can see it's a list of strings, and every string is a line of the Shakespeare text. So here we're going to take every line in the Shakespeare text and then split it by white space. And then, the line.split will return a list of all the words in that line. And then the length of that list will give you the number of words in that line. And then this list comprehension right here will give you a list of lengths of lines. And then so now you take the sum of the list of lengths of lines, and you get the total number of words in this in the Shakespeare text. Okay? Does that make sense? So did everybody get that? Okay. So I saw some shaking hands. So every Shakespeare is a list of lines of the text. Each line is a sentence, as you can see here. So like Act 1, Scene 1, London, the Palace, Enter King Henry, etc. And then so for each line, what we're going to do is split it by white space. So actually we can print that right here, right? So Shakespeare here, we can take the first line, see what's going to happen. So for a line in Shakespeare, it's going to take every element. So this is an example element, and then we're going to split it. So it's going to split it into different words by white space. And then here we take the length of this, right? Which is 2. So there were 2 words in this line. And then so this list comprehension should now give us a list. It's pretty long, but it'll give us a list of the number of words in every line. And then, so now that's a list of all the number of words in every line. Now we just take the sum of that to get the total number of words. Okay? So we can delete that and run this. And we see that there are 814,000 words in this text. Okay? This clear? Any questions? All right. So the last thing that you need to know about this is that there are also these things called generator expressions. How many of you are familiar with generator expressions? Just a few? I see like 2, 3 hands. Okay, so generator expressions are sort of like a list comprehension without the brackets. It's like one way of thinking about them. The difference between a generator expression and a list is that it returns an iterator that gives you every single element in that list. But it does not construct the entire list. And this is the key part here, is that it does not construct the entire list. So if you have something such like, if you're going to go through all the words of Shakespeare, you can see we have 814,000 words. So if we made a list of all the words of Shakespeare, then that list would be 814,000 entries long. If we use a generator expression for it, we could iterate through 814,000 words without constructing the entire list. And so that's the main reason why you need to know about this, is for performance reasons, really. So we could actually could have written the previous line here that counts the number of words without using the brackets to construct the list. So here it's the exact same generator expression. So this will return a generator expression now that gives you the number of words in every line. And then if you pass it to the sum, then it'll go through the entire generator expression and calculate the sum of everything, but without creating the entire list of all the word counts. Okay? That makes sense? Okay. We'll see why this is important in a little bit. But are there any questions so far? Okay, so now let's go to list performance things that you need to know when you're writing your code so that you don't end up timing out on Autolab. All right? So as a side note, Jupyter Notebook has these things called magic functions, which sort of do, things that are not standard to the typical Python interpreter. So for example, there's this timeIt magic function, which will actually, time your code. It'll just take everything in the cell and run it and tell you how long it took. Okay? So we're going to use this magic function to, find out how long this code takes. And so what we're going to do here is we're going to take a list. We're going to take the text of Shakespeare and turn it into a list of words. Because right now we have a list of lines, but to do processing on the words, we want it to be a list of words instead. So one way you can do this is, okay, we'll create an empty list. For every line, we're going, here, I'm limiting it to like 10,000 lines so that it completes in a reasonable amount of time in this class. And so for every line, we're going to split it into words, and then for every word in that line, we're going to insert it into the list of words. Okay? And here we're inserting it at the beginning. Okay? So, does anybody know what's wrong with this? Sure. Yeah. So the answer was that you have to move every element forward one every time you insert at the front of the list. Now this might not make sense. This might not seem like a big deal to you because you might think, oh, this is a list, right? Maybe it's a linked list, and so adding something to the front is just going to add a new pointer to the front of the list. But actually, if you understand how this list is implemented in the background, then you'll immediately see why this is a terrible idea. So just so you can see, we're going to run this, and then so this is inserting at the front, and then this second one is inserting at the back. And so here it says it takes about 1.68 seconds to run, and then the second one takes, let's see, about 13 milliseconds. So there's more than a 100 times speed up from inserting at the end of the list as opposed to inserting at the beginning of the list. And so as was mentioned, the linked list is in Python, or not the linked list. The list in Python is actually implemented as a variable length array. So it's just like your standard array underneath the hood, and then it gets resized every time it runs out of space. So if you need to insert something at the beginning, it then actually needs to move everything in that array forward one spot. And so this is why it's really important to understand how this list is implemented so that you don't start doing things that cause 100 times slowdown in your code, which starts to matter when your code is more than just string processing. Okay? Are there any questions about this? Does it make sense? Okay. So as a result, since it's a variable length array, doing things like inserting lists in the middle of another list are also going to be kind of expensive because now it has to move everything over to accommodate for the stuff that you've put in between. So really the fastest operation in a list is to add stuff to a list is to add it to the end. And since its underlying implementation is actually just an array, iterating through a list is actually really, really fast, thanks to that. Okay. So now we can take this, just for your own sake, the second example can actually be written much more concisely as this. And so we're going to run this so that we can process all the words. Yeah, and it's done like almost immediately. We're going to process all the words because actually if you run the slower example with all the words, it does not terminate in any sort of reasonable amount of time. You can try it on your own computer if you'd like. You can let me know if it completes before the end of class. Okay, so now we're going to move on to dictionaries. So dictionaries are sets of key value pairs. Similar to a list, you can initialize it by specifying directly its keys and values. It's denoted by the curly brackets notation. And you can also use a list comprehension type construction. So in this third example, we have, for every string in list 4, we're going to take the first 2 characters and map them to the rest of the string. So it's pretty straightforward. You can think, and so we can use this dictionary to count the total number of words in the Shakespeare text. So, okay. So what we're going to do here is we take the list of words here. We do the same thing that we did up there. We're going to actually process it a bit. So this is some basic string processing. We're going to basically take each word, and then we're going to turn it all into lowercase, and then we're going to remove all the punctuation. That's what this translate call does, so that everything's sort of canonical when we're counting the words. And then here I have to find a count function, and basically it's going to iterate through every single word. And then if the word is in the dictionary, then we'll increment its counter. Otherwise, if it's not in the dictionary, then we'll set the count to 1. All right, pretty straightforward. But actually, as it turns out, this takes really long. Okay, so again, we're going to run this on a limited number of words, and see what. And just limiting to the first 10,000 lines, we see that the smallest occurring words, the smallest 5 frequencies are like bagpipe, mustachio, Holyrood, and the most frequent words that show up are like the, and, I, of, a, so things that you would normally expect. So, but we're only processing 10,000 words. So does anybody know why this code is too slow to process all the words? Nobody. I have a hint. It has to do with a similar, oh yes?
Yeah, I just have a guess. I don't know exactly, but so maybe this dictionary in Python is implemented so that when you have if word in the one case, so if you want to find, you just go through all of the dictionary, but not using the tree.
Right. So what he was saying is that he's pointing out that maybe the dictionary is implemented so that you could maybe instead of searching in all the keys, you could just test for membership inside a dictionary. And actually, that's exactly right. So if you write code like this, it makes sense syntactically and it looks pretty good. But what this call does in Python 2, at least, is that d.keys will return a list of all the keys in your dictionary. And so every time you iterate through every single word in this for loop, you're creating a list of all the keys in the dictionary, which is an incredible waste. So actually, we can time it here and see how long it takes. But your intuition is completely correct. So here it takes about 300 milliseconds per loop. So now we have a faster count. So now we have, instead of if word in d.keys, we just have if word in the dictionary. And Python has overloaded the dictionary membership function so that it's much faster than creating a list of all the keys. And so this should be a faster count, so we can see how long it takes. And here it takes about 1.5 milliseconds per loop. So in comparison to almost 300 milliseconds. So that's like a 200 times speed up. Okay? Yes?
So if we put set to the debug key, is it maybe faster?
Oh, so you're saying, what if we made this like put a set here? Is that what you're saying? So yeah, the question is, what if we put a set around d.keys? And I guess the dictionary keys are already unique. So the keys to a dictionary are already unique, so it doesn't really matter that much.
So when set first bit is full one.
True. So if it is a set, then finding membership is faster, or is like logarithmic in time. However, the main slowdown here is the fact that we're literally constructing a list here. d.keys constructs a list. Right? So even if we constructed the list and then turned it into a set, the main slowdown is we're still constructing that list when we don't need to construct a list of keys in every single loop iteration. Okay.
Quick question.
Yes?
Is the slowdown in the construction of the list or searching in the list? Because
The slow,
in the dictionary,
yeah.
you'll be hashing, so that's why there will be constant time operation.
Yeah.
Right. Construction of the list, unless that list is like super big and it won't fit in memory.
Yeah, so it'll be slower on both accounts actually. So both things will cause it to slow down. So yeah, so searching through a list is also slow because you have to now iterate through the list to find out if what you're searching for is in the list. And also if your dictionary is very large, then constructing the list is also going to be pretty hefty. So yeah, both of them contribute to the slowdown of this code. Okay. Any other questions? All right. So here we're going to use the faster one to process all the words. If you want to see how long the slower one takes on all the words, you can also run that and let me know by the end of class if it actually finished. Okay, and so now the last thing you want to know is that when you're iterating through a dictionary, you still want to avoid creating lists. So like if you want to iterate through all the keys of a dictionary, sometimes it might make sense, you might think it makes sense to create a list of all the keys and then iterate through them. But instead of calling the keys function, which will create the list of keys, you should instead use iter keys, which will give you an iterator, which is similar to the generator expression that we talked about before. So it won't create the list, but it'll go through all the keys. Okay? So here we can take, we just take a synthetic dictionary, which is just 1 million elements mapped to 1 million elements. And then we're going to just time looping through every single key inside this dictionary. That takes about, and doing nothing inside the loop. So one takes about 36 milliseconds, the other takes about 20 milliseconds. Depending on the size of the keys that you have, this can become slower or faster. So it may not make a difference when you write small code, but when you start processing huge amounts of data, then you might start seeing the impacts of using the keys as opposed to iter keys. Okay, does that make sense? So long story short, when you're iterating through dictionaries, use iter keys or iter values so that you don't avoid creating lists of every single element. Any questions? Okay. Okay, and then for the Python 3 folks, actually, some people realized that having keys create an entire list was actually a really bad idea because everybody would do it not knowing that it's creating an entire list. So in Python 3, they actually updated it so that the keys of Python 3 is now like view keys in Python. Wait, the keys in Python 2.7 is now the view keys in Python 3. And now the original keys command in Python 3 is actually iter keys in Python 2. Okay, so now in Python 3 you can use keys, .keys, and .values, and it'll give you an iterator as opposed to an entire list. But in Python 2 you have to make sure you're using iter keys and iter values instead. Okay? All right, and so the last Python thing that we're going to go through is we're going to go through just how to construct the basic class. And so it's pretty similar to that of other languages. And so when you create a class, you just have to type class and then give it a name. And then all the variables inside the class have a local namespace to it. So things defined inside the class are not really visible outside of the class unless you reference it through the class. And so classes have two main usages, attribute references and instantiation. So in this first example, we're going to create a class and give it two attributes. Variable 1 and variable 2 will have a value 1 and value 2. And so you can run this and then, okay, we can reference these variable names directly by using the class name and then using a period to refer to an attribute. And then the attribute name here is variable 1, and that'll give value 1, and the other one will give you value 2. So it's pretty straightforward. So this shouldn't be new to most of you. So other attributes you can have are functions, right? Functions can be attributes as well. And so we can define some functions here. f and add variable and set variable. Now the thing about Python is that all the functions take into their first argument is always going to be the instantiation of that object. Okay. So when you create a class object, that object has an instantiation, like it's a variable, and that variable, when you call a function from that variable, the first argument will be that variable. Okay, so we can kind of see that here. So here I'm going to create a class name. It's going to have the same variables, some functions, and then I'll initialize, instantiate a instance of class name, and then when we print a.f, its first argument is going to actually be a. It's going to be the object that called the function. Okay, so all of these have to take in as their first argument the object itself. So then we run this, and we see that, okay, a.f is going to just return itself. And so we see that, okay, it returned itself. It was a class name instance. And then, okay, add variable will take the first argument, the first argument, which is actually the second argument, and then append it to the first variable, which is here. So we get string appended to value 1. And then set variable 2 will take the input string and then set it to variable 2. So it's pretty straightforward. You just have to know that functions take in the class instance as their first argument. And then so it needs to be a class instance. So if we try to just refer to the class itself and call the function here, we'll see we get a type error. So we see it says it must be called with a class name instance as the first argument. But you can actually get around that by using directly this format. So you see how it takes like f of self. Self will be overloaded to be the object that is calling the function f, unless you call it directly straight from the class name, right? So then class name here, we can pass self as a, and then that'll be fine, all right? And then that works exactly as you would expect up here. So it just returns self. It returns a. Okay. Any questions? Okay. And then, so if you don't want this like self variable in your functions, you can actually add some decorators to change, the signature of your function. So, for example, class method will allow the first argument to actually be the class name and not an instance. And then static method will just completely remove that first variable completely. So then you can just write, your functions as you would normally expect them outside of a class. So we can see an example of that here. So we have one of them is going to be a class method, so it'll be able to take in the class name, and the other one's a static method, so it doesn't need a first argument. And then so we can run all of this, and we see, okay, the first one does exactly what we thought it was, exactly what was before. The second one, we can call it directly from class name, the definition of the class. And then in the third one, we can call it, and it does not need the self. Yeah. It does not need the self here, right? We just needed the x, all right? So just some basic class definition stuff. And so in Python, there are some naming conventions and some special functions that you should be aware of. There's no truly private variables in Python. Like every single function or variable that you define in a class is viewable from outside of that class, but they do some naming conventions to sort of hide some stuff that you think are unnecessary, but somebody could actually access them if they truly wanted to. And so the convention that they have is actually a leading underscore is for sort of weak private use. So if you want to hide something but not really, then you put a leading underscore in front of it. And what that'll do is that if somebody tries to import star from your module, it'll ignore all of the things with a leading underscore. And then the double leading underscore is for stronger private use. So if you really, really don't want somebody to use a function, then you put two underscores in front of it. And what this does is when people import function, when people try to use this function, they find that they actually can't because the name has been mangled. So what they actually do is they take the name of your private function, and they add the class name in front of it. So it would be something like, underscore underscore class name underscore, then your function name, so that it's much harder to use it, but if you really wanted to use it, you could still get it, okay? And then if you have a double leading underscore followed, and then a double trailing underscore, these are Python magic functions that have a special meaning in Python that are used inside the rest of the library. So really, you should only overload these if you know exactly what they're going to do. But you will be overloading these because one of these is actually the initialization function for a class. So this init function that probably almost all of you are familiar with is the class initialization function, and it defines it is called when you create a new object. So for example, here we have class. We have a new class. We define the init. It takes in itself and a variable s, and then it's called when we run this and create a new object. So the init function is called when you create a new object. There are other magic functions. For example, the double underscore string function, which will define sort of the behavior that happens when you try to print an object, right? Because when we tried to print stuff up here, we saw we got these these things, these class name instance at 0x00. It's not very useful. So if you want to print nicer things from your code, you should overload the double underscore string function. So we do that here. We define the double underscore string function, and we're going to return class name and then the variable that's inside of it. So now we can create a class with the variable foo, and then print it, and it'll print this nicely formatted string that I made. Okay. So any questions about that? Okay. And then just putting this all together, we can now take the Shakespeare code that we had earlier, put it all together into a text reader. So then in the init, we just take in the file name, read the lines, create the list of words, and then we define a function called word counts, which returns the dictionary of word counts. And so now we can now we have a generic text reader that takes in words, calculates the word counts, and does exactly what we did before, just now organized in a class. Okay. All right. Are there any questions about that? This is pretty much most of the Python know-how that you will need for, the really important stuff is really the performance things, because if you start timing out on Autolab, that's probably the first thing I will tell you if you come to my office hours. Because I'm pretty sure most of the Autolab tests will give you will finish in less than a minute. Okay. So if it's taking longer than that, then there's something wrong. Okay. If there are no questions, then I will move on to the last section, which is making some basic visualizations using matplotlib. No questions? Okay. Am I going too fast? Is it too slow? Is it okay? All right. Okay, so now let's move on to basic visualizations. So, Zico has said this before, the most important thing that you should do once you've gotten your data is to look at it, see what's going on, and make sure everything is what you would sort of expect it to be, or expect it to be, or identify places where things are actually kind of going crazy. Okay, so a good tutorial is actually here. I'll let you go there on your own time, but to use stuff inside, to make plots inside the Jupyter notebook, we'll actually need some more magic commands. So down here, so first we'll import matplotlib. I recommend you use the SVG backend so that your plots look pretty and not pixelated. It makes the plots use vector graphics instead. And then you need this magic command, matplotlib inline, to make the plots show up in the notebook. So then when you make plots, they'll just show up right underneath the cell that you ran them in. Okay. And then the main plotting thing that you'll need is the pyplot. And the default style for matplotlib is really, really, really ugly. So I recommend that you use a different style. I just picked this one because it looked reasonably okay. And actually, and we'll comment this out for now and you can see. And then you can configure how big you want it to be. Okay. So So here it's just a very basic example. We're gonna, NumPy is just a numerical programming package that has a lot of like matrix and like math routines in it. And so this is basically just going to, take a range of numbers from -pi to pi, and then calculate the cosine and sine of those numbers, and then plot them on the same graph and then show them. Okay. Actually, this one's not that ugly. It's okay. This is okay. We'll take this back. Okay. So pretty straightforward plots. Now we're gonna go back to the Shakespeare word counts again, and we're gonna make a bunch of histograms because that's a very common thing that you do when you have a lot of data. Is just look at the histogram, see what the shape is, and understand what's going on. So here we can take plot.hist, take the dictionary of word counts, and actually just take all the values, so all the counts, and then plot the histogram of all the words. And then that shows up there. And okay, so this is not actually very useful, right? All you see is one bar, and it's pretty useless, right? So this is as it turns out, this is because almost every single word shows up one time, or very few times. And so almost every single word gets shunted into the very first bin, which is extremely large, which makes all the other bins look extremely small. In fact, so small that I don't think you can see them. Okay, so what you should do when this sort of thing happens, when you have extreme values, is to change your scale of the axes to become a log scale. And then we see it, okay, now this is much more reasonable, right? You can actually sort of see what's going on. And you just have to remember that this is a log scale. So we see immediately two things. A large number of words have a small frequency, and a handful of words have an extremely frequent occurrence. Right? That's probably the small words, like the, a, is, that we found earlier as the most frequent words. But so then this would just so then what this does is it takes all the word counts, it sorts them, and then we just take the top 5 words and print the word and the actual count, and we see that the top 5 words show up quite a number of times. Like B shows up 27 times. The other words show up around 14,000, 15,000 number of times. And then the second line says it makes a list comprehension of the number of all the words that show up once inside the dictionary, and then it counts how many there are. And then we see that actually 12,000 of the words are showing up exactly once. So this sort of just confirms what you see from the plot, that this is an extremely skewed data set, and if any of the algorithms that you use start making assumptions as to the distribution of your data, like a lot of algorithms start to assume that your data comes from a normal distribution, well, I don't know about you, but this does not look very normal to me. Okay. And actually, this may not be very useful or not, but I made both axes a log shape, and then it ended up being actually pretty linear for the histogram. Just an interesting plot. So like you can just like play around these plots and try to see if you can find some interesting stuff. And then just for fun, you can pip install word cloud and then generate a word cloud. It's pretty straightforward. They're not terribly useful in terms of doing data science, but they look nice and you can show them to people. So, like whenever people do text processing and then they have like a nice picture to go along with like an article that they wrote about it, there's always a word cloud. So word clouds are pretty easy to make. Okay, so now let's move on to a different data set, one that maybe you care about a little more than the Shakespeare text, which is the Piazza statistics of everything that we've had in the last week. Okay? So here we'll discuss how you make multiple figures, how you make scatter plots, how you layer plots on top of each other, and we'll do this with the Piazza statistics from this course. Okay? So you can go through a CSV file and process it manually. I'm using a package here called Pandas, which can read from a CSV and stores it in this data frame structure. But if you'd rather see how you can do it yourself, I put the code for how you would process the CSV file right here. But Pandas is just another scientific computing library that you can use, which is also included in Anaconda. So if you have Anaconda, then you're all set. Okay, and so here I imported the Piazza statistics. Actually, I removed the names and the emails so that nobody could see who was doing what. And you can I printed the first 5 elements in this data frame, and you can see, all right, the first 5 people have these sort of statistics associated with them. Okay. Okay. So now, as we did before, we want to make a bunch of histograms, but now let's make them all in the same figure. Because we now have 6 different categories of data. Right? We have the days online, we have the views, we have the contributions, we have the number of questions, we have the number of notes, we have the number of answers. So we want to make a histogram for every single one, but instead of making 6 different cells, we can just plot them all in the same figure. And so the way you would do that is you would just set a figure, and then you use this subplot command, okay, to tell matplotlib which part of the figure you're going to plot to. And then so the notation here, you can read it online, but it's basically number of rows is the first number, the number of columns is the second number, and then the index into this grid is the third number. So then here, I want a 3x2 grid, and then plus +1 for every, to iterate through every single grid spot. And then so in every single grid spot, I'm going to make a histogram of the data, and then I give it a label, and then I move on to the next grid spot. Okay? So we run this, and we see lots of pretty histograms. Okay? So we see the number of days online is actually relatively, it's actually a little bit normal. Number of views is pretty skewed, and number of contributions is extremely skewed, actually. And the number of questions, the bottom 4 plots, the bottom 4 statistics are basically completely skewed. So you do this, you look at your data and you see what's going on. All right, that's the whole point of this. And knowing how to make multiple figures in a single plot is also useful. So in addition to histograms, you should also know how to make scatter plots. It's fairly straightforward. You would use the plot.scatter instead of the plot.histogram, and then you would give it give it an x x data and give it a y data, and it'll plot the scatter plot. So here we're going to plot the number of contributions against every single other column that we have. And you can see the scatter plots here. And does anybody see anything interesting as we go through these scatter plots? I don't know about you, but I see this little dot out here is all the way by himself, and over here too, it's all the way by himself. There's a few extreme points here that are sort of just all the way out. All right. So you're going, we're just sort of this is sort of a toy example, but it's the type of thing that you should be thinking of when you're going through your data. Is look for any sort of anomalies and try to explain why they're there. And so actually, let's see. Yeah. Okay. So we basically walked through how you would make your own grids of scatter plots and histograms by yourself. And actually, the Pandas package has a function that'll make pairwise scatter plots and all the histograms for you. So it's mostly for convenience, really. It's this plotting.scatter matrix, and then so it does everything all together, right? But then it's good to know how to make the plots on your own, because usually at the end when you have to write your report or something or show it to somebody else, you don't actually want to show them all of this. You want to show them the parts that are important, and the parts that are relevant, and the parts that you want to highlight. So this is why we're walking through how you would actually create these yourself. But if you're just doing some exploratory analysis, then using a built-in thing just to see what's going on is perfectly good enough. So we see that there are a number of extreme points, and the reason is because I left the instructors inside the Piazza statistics. So actually, as it turns out, these top four, let's scroll back up. These top four entries are actually the instructors. One of them is me. So if we actually take away the first four instructors and then plot them, and then we see that the scatter plots are much more evenly dispersed, which is more what you would expect along these. Well, some of them are still skewed, but they're not as badly skewed as they were before. Okay, so the last part is that we can also overlay plots on top of each other. So, because in all of these examples, we sort of just made one plot per square, but sometimes you'll want to put multiple plots or like multiple lines on a single image. And then so what we're going to do here is actually we're going to take all the student contributions and we're going to fit a geometric distribution to them, which has the amusing connotation that if a student follows a geometric distribution of posting on Piazza, then that means they have a probability p of never posting again and a probability 1 minus p of posting again on Piazza. If you believe this model. No, this disclaimer, this is not, it may or may not be what we actually use to estimate the distribution of this class. But we're going to fit a geometric distribution and then plot the geometric PDF on top of the histogram, okay? So here we're just calculating the PDF, and then first we plot the line, and then underneath it we plot the histogram of the contributions, and then we show, and we get something like this. It's kind of big. That's okay. So then the distribution is the red dots, and the histogram itself, the actual histogram, is the blue bars. And then for your own entertainment, I went ahead and calculated the standard deviation for this distribution and the mean, which comes out to a cutoff of about 0.64, just for your own amusement. So the very, very last part, okay, I promise this is the very last part, is matrix visualizations. So when we give you like a matrix and you want to like figure out what's going on, it's not quite so obvious as to how you would make this into a scatter plot, or maybe your matrix is like 1,000 features by 1,000 entries, and like making pairwise scatter plots of 1,000 features is probably not the smart thing to do, right? Because then you'll fill up your screen with all these tiny little scatter plots, and you'll waste your time doing that. But one thing that you can do to visualize these matrices is to make these heat maps, okay? So what we're going to do is we're going to take this data frame of Piazza posts and create this covariance matrix. If you're familiar with a covariance matrix, then great. If you're not, then that's okay. You'll get to it later. And what we're going to do is we're going to use this command called imshow to create a heat map of the matrix. And by heat map, I mean something like this. So now the idea of this is that lighter, the intensity of the squares corresponds to the actual value within that matrix. So then here, so the actual covariance matrix is here, and we can see that views with views is actually really high, and everything else is actually not that big. Maybe views with contribution is getting there. And so down here we can see that it's a little too big for the screen, but the views with the views, so that's the second column and the second row, is this white square. And so that this correlates the values of the matrix entry with the actual intensity of the image being displayed. Okay. So are there any questions about that? So this is how you would usually look at your matrices and sort of figure out what kind of structure is going on here. Like maybe you've got some very dense blocks here with high values, and then actually most of the matrix is actually empty with like very small values. All right. If there are no questions, then this is the end of the tutorial. I hope you found it at least somewhat useful, or very useful if you are very new to Python. Yes, question.
Are there any limits to like plotting libraries that you'll be able to use? Like generally, are we going to be asked
So the question was, are there any limits to any plotting libraries that you can use? And I don't believe we're going to put any limits on the libraries that you'll use. For the most part, you'll use matplotlib because it's the easiest and most straightforward thing to do. But I don't believe there's going to be any sort of restriction on what you can use to visualize your data. Yeah. In reality, it should just be whatever you can use to make it look best and get the most inference about your data. Did you have a question? Okay. Are there any other questions? All right, if there are no other questions, then that's the end of the lecture. And good luck on your homework. Yes, in the back. It's already online. Yeah, the notebook is already online. All right, thank you.